A-star search works by always expanding the path that has a minimum value of the function f, which is defined as the sum of the g and h components. Now the function g of a path is just the path cost, and the function h of a path is equal to the h value of the state, which is the final state of the path, which is equal to the estimated distance to the goal.
The title of this page is A-star search. The first line is f equals g plus h. The second line is function g of path equals path cost. The third line is function h of path equals h of s equals estimated distance to the goal.
Here's an example of how A-star works. Suppose we found this path through the state space to a state x, and we're trying to give a measure to the value of this path. The measure f is the sum of g, the path cost so far, and h, which is the estimated distance that the path will take to complete its path to the goal. Now, minimizing g helps us keep the path short, and minimizing h helps us keep focused on finding the goal. And the result is a search strategy that is the best possible in the sense that it finds the shortest length path while expanding the minimum number of paths possible. It could be called best estimated total path cost first, but the name A-star is traditional.
The first line is A-star search. The second line is f equals g plus h. At the bottom, the figure shows a starting state S on the left and the goal state on the right. There's a state x in the middle and a path connecting S and x. The cost of this path is g. There's a dotted line between x and the goal.
Now let's go back to Romania and apply the A-star algorithm, and we're going to use a heuristic, which is a straight line distance between a state and the goal. The goal again is Bucharest, and so the distance from Bucharest to Bucharest is of course 0. And for all the other states, I've written in red the straight line distance. For example, straight across like that. Now, I should say that all the roads here I've drawn as straight lines, but actually roads are going to be curved to some degree, so the actual distance along the roads is going to be longer than the straight line distance. Now, we start out as usual. We'll start in Arad as the start state, and we'll expand out Arad, and so we'll add 3 paths. And the evaluation function, f, will be the sum of the path length, which is given in black, and the estimated distance, which is given in red. And so the path length from this path will be 140 plus 253, or 393. For this path, 75 plus 374, 449. And for this path, 118 plus 329, 447. And now the question is, out of all the paths that are on the frontier, which path will we expand next under the A-star algorithm?
The distance from Arad to Ziran is 75. The distance from Arad to Cebu is 140. The distance from Arad to Timisoara is 118. The estimated distance from Ziran to the goal is 374. The estimated distance from Cebu to the goal is 253. The estimated distance from Timisoara to the goal is 329. So, f of Ziran is 449, f of Cebu is 393, and f of Timisoara is 449. Which city should be expanded next?
The answer is that we select this path first, the one from Arad to Sibiu, because it has the smallest value, 393, of the sum f equals g plus h.
This page shows the road network in Romania. The title is A star. H equals straight line distance. The distance from Arad to Cebu is 140, and the straight line distance from Cebu to the goal is 253. So, the cost of Cebu is 140 plus 253 equals 393.
Let's go ahead and expand this node now. So we're going to add 3 paths. This one has a path cost of 291 and an estimated distance to the goal of 380 for a total of 671. This one has a path cost of 239 and an estimated distance of 176 for a total of 415. And the final one is 220 plus 193 equals 413. And now the question is, which state do we expand next?
Now the frontier has Ziran with cost 449, Aradia with cost 671, Phagros with cost 415, Timisoara with cost 447, and Arbi with cost 413. Which city should be expanded next?
The answer is we expand this path next because its total, 413, is less than all the other ones on the frontier, although only slightly less than the 415 for this path.
RV should be expanded next because its cost 413 is the smallest.
So we expand this node, giving us 2 more paths. This one with an F value of 417, and this one with an F value of 526. And the question again, which path are we going to expand next?
Now the frontier has Ziran with cost 449, Aradia with cost 671, Phagros with cost 415, Timisoara with cost 447, Pitasti with cost 417, and Craiova with cost 526. Which city should be expanded next?
And the answer is that we expand this path at Phagros next, because its F total, 415, is less than all the other paths in the frontier.
Phagros should be expanded next because its cost 415 is the smallest.
Now we expand Phagros, and we get a path that reaches the goal, and it has a path length of 450 and an estimated distance of 0 for a total F value of 450. And now the question is, what do we do next? Click here if you think we're at the end of the algorithm, we don't need to expand next, or click on the node that you think we will expand next.
Now the goal Bucharest has F value 450. What should we do next?
The answer is that we're not done yet, because the algorithm works by doing the goal test when we take a path off the frontier, not when we put a path on the frontier. Instead, we just continue in the normal way and choose the node on the frontier which has the lowest value, and that would be this one, the path through Pitasti, with a total of 417.
Pitasti is chosen to be expanded with F value 417.
So let's expand the node at Pitasti. We have to go down this direction, up, and then we reach a path we've seen before. And we go in this direction. And now we reach Bucharest, which is the goal. And the H value is going to be 0 because we're at the goal, and the G value works out to 418. Now again, we don't stop here just because we put a path onto the frontier. Rather, we put it there, we don't apply the goal test next. But now we go back to the frontier, and it turns out that this 418 is the lowest cost path on the frontier. So now we pull it off, do the goal test, and now we found our path to the goal, and it is in fact the shortest possible path. In this case, A star was able to find the lowest cost path. Now the question, which you'll have to think about, because we haven't explained it yet, is whether A star will always do this. Answer yes if you think A star will always find the shortest cost path. Or answer no if you think it depends on the particular problem given. Or answer no if you think it depends on the particular heuristic estimate function h.
The question is whether A star search is optimal. There are three choices. The first, yes, always. The second, no, depends on problem. The third, no, depends on h.
The answer is that it depends on the h function. A star will find the lowest cost path if the h function for a state is less than the true cost of the path to the goal through that state. In other words, we want the h to never overestimate the distance to the goal. We also say that h is optimistic. Another way of stating that is that h is admissible, meaning that it's admissible to use it to find the lowest cost path. So think of all of these as being the same way of stating the conditions under which A star finds the lowest cost path.
The first line of this page is A star finds lowest cost path if, and there are four statements which are equivalent. First, h of s is less than true cost. Second, h is never overestimate. Third, h is optimistic. And the fourth, h is admissible.